Good afternoon, dear students. We can start. Can you hear me? Okay, thank you. Thank you for feedback. So, in our last week lessons, we talked about the electromechanic actuators, mainly relays and the electric motor. And we discuss how can we select the electric motor. Actually, what is the main parameter to select an electric motor, like we learned in pneumatic and hydraulic actuators. So, and we learned that in electric motor, if we select an electric motor, first of all, the important part is the power and power, torque, and the RPM, I mean the rotation per minute, speed. So today we will continue with electric motor, the actuators of electromechanic actuators, that means the electric motors. And another important part to select an electric motor for our application is the gearbox. Gearbox is also one important component in application of the electric motor, because you know the electric motors sometimes deliver a certain RPM, I mean the speed and the torque based on the power, but in our application, it could be that we need different torque, or the torque we have to decrease the speed of the electric motor and increase the torque for the application. So there is a video about the selection of electric motor concerning the gearbox. So first of all, let's watch the video. And I have to share the screen with you now. The screen, okay. Hold on. So let's watch the video. Okay.
Hi, this is Janet
and Joe
with Grow Shop, and welcome to our Gear Motor Basics series. In this video, we get to the heart of the topic of gear motor selection with two methods for pairing motors and reducers to create the optimal gear motor for any given application. In this first method, we'll look at how you select a gearbox, select a motor, and then put the two together. In method 2, we'll take a look at selecting a pre-engineered integrated gear motor. It's probably not surprising to you that the first method takes more work. However, we think it's important you understand the engineering that goes into the optimization process of matching a reducer and a motor, even if you're choosing an integrated solution.
From our experience, the best method for configuring the optimal gear motor is to start by selecting a gearbox that will give you the right speed and torque output requirements for an application. Then, working backwards from the gearbox selection, we select the motor that provides the appropriate speed and torque inputs for the selected gearbox, the motor outputs. Once the motor is selected, the actual speed, torque, and efficiency need to be calculated. This chart assumes the motor and reducer reference charts we shared in previous videos and have included the links below have been used to make some basic type selections. Then you need to refer to the manufacturer data for those components to make the calculations. Let's take a deeper look at these steps. Realize the whole process may require several repetitions to determine the optimal gear motor combination. For the sake of time, we won't repeat the often multiple process repetitions.
Let's assume the application speed and torque have been determined. This is step 1. And now we're ready to start by selecting the reducer. When reviewing manufacturer data for reducers, the ultimate goal is to find the output torque, which leads to the proper reducer size. The amount of torque the reducer will be able to produce is dependent on what we call primary reducer data, the efficiency curve, life curve, thermal rating, and maximum input speed. These 4 specifications allow us to determine when a reducer's output torque is limited by thermal or mechanical constraints.
Notice we aren't talking about reducer ratios at this point. Even though it will impact the torque rating, it's typically determined later in the process during the motor selection. The first step to determining output torque is to match the life requirements of the gearbox using the gearbox manufacturer's life curve. The curve illustrates the load a gearbox can withstand over time based on the mechanical strength of its components. Be aware that the time range on the x-axis, 0 to 8,000 hours, varies from manufacturer to manufacturer depending on their gearbox type and testing protocols.
The life curve also gives us yield strength, which is the torque value where the components of the reducer will fail. This life curve is an example of a continuous duty life curve. There are no adjustments made to the reducer's life for other conditions such as side loading, which would affect the output bearings, or temperature, which would affect both lubrication and duty cycle.
Next, we need to look at the efficiency curve. It's important to review these curves when making a reducer selection, so be sure to get them from the manufacturer. Our sample curve is for a planetary gearbox and is a graph of torque versus efficiency. It's important to emphasize that efficiency is not constant with torque. This data is used to calculate the torque capacity of a gearbox from a thermal standpoint. An important observation to make from the graph is that selecting a gearbox that is too large for the application will result in operating in the low efficiency range of the curve. For instance, using this gearbox in an application with less than 50 inch-pounds of torque is extremely inefficient and is not using the gearbox to its full potential. A reducer that will operate at peak efficiency in the continuous torque region for the application needs to be selected.
Now we determine the maximum heat that the gearbox can dissipate at the maximum temperature the gearbox will allow. This is known as the maximum allowable dissipated heat, or energy. The heat generated in the gearbox is a function of its efficiency and is determined from testing and theoretical calculations. Once the maximum allowable dissipated heat is determined, the dissipated watts, or energy, at the application load point and efficiency needs to be calculated. Then it's compared to the maximum allowable dissipated energy.
This series of equations compares the calculated dissipated watts to the manufacturer's specified maximum allowable dissipated watts and ensures that the calculated watts do not exceed the maximum allowable watts. First, the output power is calculated using the speed and output torque requirements of the application. Next, using the efficiency at that output torque, calculate the dissipated watts. Then, make sure it falls below the maximum allowable watts as specified by the manufacturer.
So, we've collected all the data that we need for reducer calculations to determine the mechanical and thermal limitations. We have an efficiency curve determined by the yield strength and continuous duty torque, as well as we determined a thermal capacity. This data allows us to select a suitable family of gearboxes that could meet the application if matched with the right motor.
Up next, we discuss selecting a motor to pair with our reducer. Check out the link below for our gear motor selection chart. And as always, for more information about GrowShop or any of our gear motor products, check out our website at www.growshop.com.
Are you a professional looking to immigrate legally to the
Okay, so we watched the video and we have seen that the gearbox is also an important part. The gearbox is also an important part regarding the electromechanical actuators, because to select the electromechanical actuators in this case means electric motor. So we need where we are going to apply that. So let's say we have a machine somewhere. Here we have a machine somewhere, and this machine in this machine we are going to use electric motor, and there is a maybe a rotary actuator needed, and for this rotary actuator we are going to use the electric motor and so on. And here we have, let's say, the type of we have an electric motor. Electric motor we are going to use somewhere. So this is not actually what I want to do. So no. So the electric motor, okay. So let's say the electric motor, we are going to use an electric motor. So then, but so it is not that what I want. Okay, this is correct now. So let's use the release, okay. So, and let's say we have an electric motor here somewhere we are going to use, and this electric motor has a certain power. And actually the power of electric and the N RPM and the efficiency of the motor is very important parameter. So we need, but the power from our application, we have to know the torque. So how much torque we need, and of course also the speed. I mean the RPM. So if the electric motor doesn't meet our expectation regarding the torque and speed, velocity, so we have to use a gearbox in between. So that means this is the gearbox and the gearbox. So the electric motor, this is the P electric we apply in, and then here we have the torque required for our application, and also the angular speed for the N. And what is the main function of a gearbox? Let's say this is a gearbox. So the main function of the gearbox is to provide the torque, the expected torque. This is the output here, which we need for the machine, which is the in for the machine. So of course in our previous lessons we learned how can we calculate the needed torque based on the external loads and the mass moment of inertia. So if we know the torque, and then we can select according to our needs regarding the torque and speed, we can select the gearbox, and the gearbox has to be connected to the electric motor. Of course, the electric motor and the gearbox and the connections to the machine must have or fulfill certain expectations or requirements, so that we can use the electric motor in the machine. Okay, so the machine side we discussed in our previous lessons regarding the torque we needed and the speed, velocity, and so on. And regarding the torque, we said torque consists of two parts. Torque total is equal torque external load, let's say external load, plus torque mass come from the mass moment of inertia. So that is G mass moment of inertia times alpha. If there's acceleration, that means the speed. If there is a speed change with time. So this is the torque we have to calculate coming from the external load and the mass moment of inertia because of the accelerated speed. So then if we know that, this torque, then we can select a gearbox accordingly that deliver us required torque. So then we have to select also a suitable electric motor for the gearbox, because the gearbox has also had certain torque and speed. So gearbox mainly convert input torque into the output torque and the input speed into the output speed. I think you learned already in the machine design part, machine design 2, because in machine design 2 we discussed the gear system and gearbox. Okay, now let's come. I'm going to share the screen with you and turn on the slides. So and we will continue with electric motor. We will close these chapters today. So this is and the 10 here and principle of mechatronics. Okay, so the actuator and the electrical actuator. Okay, we are here. So can you see the PowerPoint presentation? Okay, you see that. So let's continue. We actually learned in our last lesson how the electric motor is working and so on. The working principle we all discussed, and you see the DC electric motor and the principle of the rotation of the electric motor. So we discussed already. And today I will. So this is how the electric motor principle of the electric motor is running. The functionality. Okay, so there is different type of electric motors. Regarding the type of motors we have here, the synchronous motor as AC motor, or asynchronous motor, and they have different properties regarding the torque and the speed, and also behavior under the last. So therefore, as for asynchronous motors, its output is from 0.1 kilowatt the more than 1,000 kilowatt, and the price level is let's say the low. And asynchronous motor, you see the functions of the motors here. The three-phase current, it works. So and it has slip effect, but I will not go into the deep. This is not so important for you. And typical characteristic curve regarding the torque, for example, here we have the torque. You see, depending on the here the N is the speed. So here we have ms starting torque is somewhere here, and then here breakdown torque, the mn somewhere here, breakdown goes down, and here nominal torque we use. I'm in the nominal torque. This is the nominal torque value. We can say this is the nominal torque value. So we can use the electric motor in this torque if we select, I mean, for our applications. Okay, so Here we can change the speed of the electric motor using the frequency inverter, so frequency converter. So if we change the frequency, so that means we can change the speed of the electric motor. And here, let's say in this area, let's use the so in this area, you see we have more or less this constant speed, but after a certain speed, so the torque is going down like this. So we have to consider if we select an electric motor. So for constant torque, we have to use these areas, this area. That means this is the nominal value of the speed RPM. So till nominal value, we can use the electric motor. So you also have listen from the video, our video, how can we select the electric motor with the gearbox. So there are also brushless servo motor. So as actually the electric motor as DC, and as we can divide in two types of electric motor based regarding the current. One of them is the AC and the other one is the DC, direct current and alternating current. And today's in industry we use very frequently the AC motors. That means the is derived with alternating current, and the DC motors can be also divided in synchronous motor and asynchronous motor, and the servo motor and the step motors. And so here the brushless servo motor, we use 0.1 kilowatt till 1000 kilowatt, and price level is higher price level as higher price is indicated. And the design wise is the stator coil package and the rotor permanent magnet. The rotor has permanent magnet. That means the coil, the stator doesn't have the permanent magnet. We apply the current to the coils in the stator, and rotor we have the permanent magnets. So and we can calculate the RPM, the servo motor using the stator rotational frequency and the rotational speed. So we can calculate the rotational speed based on this stator rotational frequency. That means if we change the frequency, we can change the speed. So you see the speed here, and is the function of the frequency. Here is this. That depends on the frequency, and if we change the frequency, we can change the speed. Okay, here you see we have a certain frequency. That means the frequency, the phases are repeating in a unit of time. And if we change the frequency, we can change the speed. And of course, if you use the servo motors, the servo motors, the important part is the resolver. So resolver, that means we can observe the electric motor, check, get the data about the electric motor regarding the motion. So is it turning left and right, or the speed, and so on. And we can control the speed. We can increase the speed. We can reduce the speed depending on the data we get. Like so, you know, we already discussed in our last lesson. So let's say this is the time axis here, and this is the speed of the motor. Let's say the RPM or W. So depending on frequency, so then we know that at the beginning, the speed is 0, and from 0 to a certain value, and this is, let's say, the nominal speed, and we derive it nominal speed, and then if we want to stop the motor, so we have to bring down the speed to the 0, and this is our nominal speed. So n and nominal n, and here in between we have acceleration. That means to bring the motor into the desired level of the speed. So therefore, here also the time is for the brake. So, and we have here the acceleration, and that's also discussed in our previous lessons. So because of the acceleration, we have mass moment of inertia, and some part of the torque, the acceleration torque, come from this part, acceleration or deceleration. So all this type of information we can get from regarding the speed, we can get from the resolver or servo motor controller. Depending on the resolution, we can control the motor very precisely. So if you have a very precise resolver, so that means we can get precise information data, and based on this precise data, we can control the motor. Okay, here you see the resolver for the servo motor control. Here the rotating coil, you see the rotating coil and induce input signals in sine and cosine coils, and here is the cosine and sine coils offset 90 degrees from each other inside, and this is the transmitter coil here the inside. So, an equivalent circuit diagram. So this is the circuit diagram we use to apply the resolver for servo motor. Another type of motor, the stepper motor. Stepper motor is not, let's say, the precise like the servo motor, also regarding the control. But in some application in the industry, it is satisfying that we use the stepper motor. And if we need, let's say, the more accuracy regarding the position or regarding control the torque or speed or repetition concerning the position, so then we have to check which one is suitable based on the application. Maybe we will use servo motor or the stepper motor. So the stepper motor is a little bit cheaper comparing to the servo motors. It has also design-wise stators, that means the coil packs, and the rotor permanent magnets, and the torque-wise up to 10 Newton meters. So not more. You see, this more if you need more, maybe say then we have to consider the servo motor. So price-wise, low price level regarding the servo motor. And you see here the rotor. Okay, here you see the inside is the rotor, and we have the coil here on the stator, and is connected to the current, to the voltage. And since the voltage is changing, that means the alternating current. So, and we have here the NS pole. You see, located on the rotor. So here, if we have here the N and we have here the S, and NS in relation, it turns in direction left or right, depending on on the current we apply. So, okay. There are different type of stepper motors like reluctance stepper motors or permanent magnet stepper motors, different design, and the hybrids in between. The hybrid stepper motor is the also combination of both. So, okay, the hybrid stepper motor, you see the picture from the hybrid stepper motor. This is the stator and the rotor. And here you see the first magnetized gear, South Pole. So gear is also important part of an electric motor. If you apply the electric motor, if you use the electric motor, so the gearbox is also very important, as we discussed at the beginning of today's lessons. So okay, here the second is the second magnetized gear, North Pole, and the stator without pole and rotor. So, and here determine the step angle, and so you can determine the step angle and the both, because you know the stepper motor moves step by step. So that means if you have the quite well resolution regarding the steps, and that means we can control the motion quite precise, and therefore the determining the step angle and tooth also very important. So we can determine the step angle tooth and using these equations here. Conditions for rotor tooth count. So rotor tooth count and the stator tooth count may not be the same and must be multiples of the pole count for each phase. So example for step angle calculations you see here, we have given is two-phase stepper motor in bipolar operating, 50 rotor teeth, and then here 4-phase due to bipolar operations, and 4-phase times 50 teeth, and is equal 200 steps per revolution. So then that means per revolution we have 200 steps. So that means we have not for each degree 1 steps. That means if we have normally, you know, for a full rotation we have 360 degrees. So if we have say 200 steps, that means we have not a step 1 degrees. That means we cannot control this electric motor, stepper motor, with the accuracy of 1 degrees. So and you see per step means 1.8 per step, so 1.8 degrees. So that means 1.8 degree is 1 step. If we say to the electric motors, is you have to turn 1 step, that means 1 step it turns 1.8 degrees. So we cannot say turn 1 degrees. It's not possible. For that we need more resolution. Here we need more teeth. I mean, maybe if we have a 100, so 100, then that means so 100, and that makes 4 times 100, 400. So 400. So we can control 1 degrees. Huh? Okay. So example for rotor tooth count. So given two-phase stepper motor, bipolar operations, 8 poles and 5 teeth per pole, and find number of rotor teeth. So the number of stationary teeth is 8 poles times 5 teeth is 40 teeth, and 8 poles and bipolar operations, 2 poles per phase, since number of rotor teeth 40 multiplied of 2 is equal 550 is a possibility. So behavior of the stepper motors, here the maximum torque, you see the stepper motor is the maximum torque. It is interesting. Now this is the HMH, the maximum torque here, and this is the MA raster corresponding to a tooth-to-tooth spacing, MH. So the maximum torque with displacement of 1/3 angle of rotation of the rotor. So the minimum torque is with the displacement of half the angle of rotation of rotor. So minimum error spacing between two equivalent magnetized rotor teeth for two-phase motor with 50 rotor teeth is around 3.6 degrees. Okay, another type of electric motor is the linear. This is the linear motor. It is developed later. I mean, you know, the electric motor we know as a actuator provides the rotary motion. Electrical actuator provides rotary motion, but nowadays we have also linear motor, like worked step by step. So only North Pole rotor teeth are considered, since statically only South Pole occurs in the stator. So you see the load torque is applied to the rotor, and the peak torque 1/3 R rotation. So let's compare of the stepper motor and the servo motor. This is actually more important for you for the applications. So where we can, what depends on application. How can we select the right motor? Regarding the the properties, and then shall we choose a stepper motor or the servo motor? So what are the criteria and how can we decide? So first of all, the peak torque. And you have seen also in the video, they explained that torque is very important to decide, especially torque is coming from our application, from the machine. The amount of the torque we need for the machine. So depending on the torque, stalling possibility with overload, step loss. So we can lose the step. So in case of stepper motor, in case of servo motor, 2-3 times overload for approximately 3 seconds. Overload is possible, but in case of stepper motor, we lose maybe we lose the steps. So from the side of dynamics, that means Vmax over Amax. V is the velocity and A is the acceleration. That means the proportion between maximum velocity and the maximum acceleration. So you see here, high for short stroke, small for long stroke. So if you have short stroke, okay, but long stroke, this is not high dynamic, but it is very high for the servo motor. So if you need dynamics, very high dynamics, that means the ratio between maximum speed, maximum velocity, and maximum acceleration. So that maybe we have to consider the servo motor. So price-wise, so stepper motor is inexpensive. So we see also from the restricted application area, but in relation to that, so the servo motor is approximately 30–50% more expensive than the comparable solutions with stepper motor. So controller technology, so controllability. I mean, how it is, which one is more controllable? That means the comfort of the controllability. And you will see now the open loop, no feedback. So mainly the stepper motor doesn't have the feedback, doesn't give the feedback for the closed loop control, and therefore the open loop control. Of course, you can apply the resolver, and you can check the motion of the rotor and get data about the motion of the rotor. But it depends on the steps, I mean, accuracy. So it is not comparable. That means in that sense comparable with the servo motor. So the servo motor has a closed loop control and feedback with a resolver. So that means the accuracy is very, very good, and also controllability is also very good. So torque-wise, so high torque with low speed. So high torque, but with low speed, and high stalling torque. But on the other side, if you use the servo motor, so constant at every speed. It is very interesting. Constant at every speed, constant high torque. So here, high torque with low speed. That means the torque speed has changed. So high torque, low speed, that means low torque, high speed is possible, or high torque, low speed is possible. But if you use the servo motor, you have a constant moment for each speed. So that means the constant high torque. And you see, those are the important parameters to select an electric motor. Let's say if we consider stepper or the servo motor regarding our applications. So the torque is important one, and the dynamic of the motors, also the price also is also important, and controllability. So is it how can we control it? And the torque, of course. Here the peak torque, and here is torque. So comparison of torque curves for stepper motor and the servo motor. You see here there's a two graph. So here we have the speed range from 0 to 1,800 RPM. Here we have speed range from 0 to 6,800 RPM. So it is quite high here. And you see here the behavior of the torque with rotation RPM here, 10,000 here, it stopped here somewhere, and we are here. This is the 100, 200, 200, 300, and so on. So in that area, so the stepper motor, full step motor, half step motor, you see the behavior of the torque. So we can use in that area. So in that area, but from this area onwards, I mean, it gets critical because torque is changing here with the speed. Torque is changing with the speed. And here you see we have the speed from here, from let's say from 500 to 9,000 and so on. And we have here the peak torque is constant, doesn't change. And the torque we use here, the nominal torque, is also not fluctuating too much. So in that area, so in that area, so it is not fluctuating too much. More or less, we have constant torque for a certain interval of RPM. So the linear motor, the working principle of the linear motor, you see here we have the connections of UVW, that are the alternating current phase. So, and then the magnet poles are changing, and there's an iron rod, and then there's a part on that is moved. So here we have you see the three-phase coils, and the moved magnet, and we achieved the linear motion. So it goes left and right. And it's an interesting development in electromechanical actuators. So motor controller, current regulator for stepper motor. So current regulator, if we have, let's say some fluctuation regarding the current, so we need the current regulator. Like this here, you see current flow in coil and current flow in coil here, so must be regulated. And so at the end, actually, this is not so important to talk about the theory of the electromechanic actuators, I mean the electric motors. But you should know what type of motors are existing in the market, like AC motor and DC motor. DC means direct current, AC means alternating current motor. And the alternating current motor used much more frequently in industry because of the requirements of applications. So, and alternating current motors, we have synchronous and asynchronous motor, and we have stepper motor, we have servo motor. So depends on application. We discussed also the properties. So asynchronous and synchronous motors are cheaper if you compare to the servo motor and stepper motor, but the controllability is not so much, not so comfortable like the servo motor and stepper motor, for example. And therefore, really we have to consider the application, which type of application we have, what do we need for the application, what are the requirements regarding the application, and so on. And therefore, we select the electric motor. But also, there are a lot of let's say there are some producers of electric motors, and they have also software. They developed also software. So if you want to use an electric motor in your machine, or you design a machine and you want to apply electric motor, install an electric motor, and you are not sure, so what should I select, and so on, then I would say you have to check which electric motor company is working with your company, and then you have to invite the people, talk about that, and let them make the presentation and about their electric motors and electric driving units, and the price and the properties and the performance, all those things. And of course, you should get also their advice regarding your application, because they are experts about the electric motors. So not only interested, of course they are interested to sell, but they should know also the applications. And if you then don't know, if you let's say meet somebody from a company representing the electric motor producer, and if you recognize that he is not expert about the electric motors, cannot help you regarding your application, so that means you have to change it. So because it could be that it's a mislead, and therefore you make a mistake. So you have to find the right one. Mainly the international, the powerful companies have very good project engineers or technical advisors, so they can give technical advice about, they can inform you about their technical products, and also help you how you can apply the product in the right way. So we have here some stepper motors, type of stepper motors. So they are classified 40, 42, 57, and 87, and so on. This is the electric motor from the company of Festo. You can see on the etiquette there. Why I have that? Because I worked many years in this company, and I have the examples from this company, and that's the reason actually. And so beside of the electric motor, they have also linear axis, like you see here. This is an axis, linear axis here. This part is moving and connected to the teeth belt inside of this body, and we connect the electric motor from here, from this part, from this side, and then the electric motor drive the teeth belt, and this belt move the part on this part on the linear actuator here, left and right. So you can control the speed, you can control the position, you can control the torque, you can adjust the ramp, I mean the acceleration and deaccelerations, all are possible. And there are different type of, let's say, solution coming from the company. Here you can use the electric motor here, and it is already connected to the linear axis. If you need a linear motion like this here, I mean, in this example, this part is moving. So this is moving part. Is moving left and right. This body is moving left and right. And here in this example, only this part is moving. We fix the body, and this part is moving. So here, that means we fix this part is down of the cylinder here, down part. So we fix it to the motor, and the motor and this part is staying and stationary, and this is mobile, and this moves left and right. So again, depends on the application. So there are also the other type of, I mean, the standard combination of linear accelerated stepper motor. You see here the you can use stepper motor. It's also possible. Or of course they have motor controller, motor driver. So if you have a stepper motor, servo motor, you need controller, driver, and so there are also some types of servo motors here, 55 and 70 and 100, and it's also 100. This is 3S, 5S, different properties and so on. So actually that's all what I want to tell you about the electric motors. So let's make a break, and after a break we will come again, and we will start to talk about the sensoric, because with these lessons we completed the actuators part of the actuators. You know, the actuators, we said this is the first part we discussed in these lessons, and then we will continue with sensors and network and hardware and software. So now we are going to start. Now the next lessons we will start with sensors. So where we are now? So okay, let's make a break. It is, let's say, 14:10, and we will start 14:25 in 15 minutes. After 15 minutes, 14:25 we start. So let's continue. As I already mentioned, we'll start now with the sensor, but before we start, maybe I can make a short introduction.
Hocam,
Yes.
hocam en son hidrolik aktüatörleri yüklemiştiniz de slaytları yükleyebilir misiniz oralarını?
Evet, tabii. Bu elektrikle ilgili kısmı yükleyeceğim, evet.
En son hidrolik aktüatörler.
I will share. Okay, I will share the last slides at the end of these lessons.
Okay, thank you.
You can get it. Okay.
Üstüne not almak daha iyi oluyordu hocam, o yüzden.
Okay, no problem. I have to. Okay, 1 second, please. Okay, let's. It must be actually possible to. No, not that. Okay, this was. Okay, it works. So you may remember we said at the beginning of the semester regarding our lesson, we said so we talked about a pentagon like this, pentagon of automation, and this is the actuator. So actuator and the sensors, and then network and hardware and the software. And as actuator, we said it could be pneumatic, could be hydraulic, and could be electric. Actuator means the motion provider, linear motion or rotary motion in this case, in this context. So then we said also, if we have a motion somewhere, linear or rotary, we need information in order to automate it. We need information about the motion. So if we say, let's say if we have a linear actuator, let's say the pneumatic actuator, like this here, a linear cylinder, and we should know the position of the piston. The position of the piston, that means so the position, okay, position, is it somewhere here or there? And therefore we use the sensors. Sensors, and we use, let's say, the B1, B is sensor used for the sensor, 1B2, how this is the sensor for the checking of advanced position. This is the initial position. So we are going now to discuss the sensor, part of the sensor, what type of sensors we have, and how can you use it, and where can we use it, depending on the application and so on. So let's come to the lessons. I'm going to share with you this screen. Okay, the sensors here. So sensors means, of course, signals provider, information provider. And this information could be digital, could be analog, could be, let's say, like on-off, existing or not existing. So first, maybe we discuss this part. So signals means, if we consider like we have seen a linear actuator, pneumatic cylinder. So this is the pneumatic cylinder, or pneumatic cylinder linear actuator. And here we have a sensor, and here we have also another sensor. And let's say this is the B1, and this is B2. So B2, what type of information we need for that? We want to know, is it this piston? I mean the piston, let's use another color for that. Here maybe you can use that. It's the piston here. Where is the piston? So we have to check the position of the piston. So is it here or is it there? So therefore, our need regarding the information is existing or not existing. I mean, the information, info, like 0 or 1. If it is 1, okay, the piston is, let's say, in the position of B1. If it is 0 regarding that, the piston is not in the position of B1, and so on. So that means this is the type of signals, let's say, signals like over the time. Let's use different color. Let's say this is not existing. So it is existing and continuing, and is not existing, continuing, existing, continuing, and so on. That means this level is, there is a signal, this is the 1, and this is the 0. So, and it is enough for us. I mean, it is enough to know, is it existing or not existing? We say binary signals, on-off type of signals. In some application, it is not enough. So we should know, so beside of the existing or not existing, we should know also the magnitude of the signals. That means if we consider the temperature, for example, so let's consider temperature. Temperature, okay. So it is not enough to, let's say, yeah, it is existing or not existing. So we should know actually about the magnitude. So what about the temperature? Let's say the weekly temperature. This is the time here. And this is here, let's say the Monday. And Tuesday and Wednesday and Thursday sorry, it's Tuesday and Thursday and the Friday and so on. So we should know the temperature. Is it, for example, it is going like this, temperature is going up and down. So, and that you have to know. So Monday is, let's say the 20, and then here somewhere Wednesday is 18, and here we have 26, and so on. Huh? So that means 1 or 2 is not enough. So like temperature, or let's say temperature or pressure, or flow rate, and so on. So then we need the analog signals or digitalized analog signals. That means we need also the quantity. So in case we check the rotation of an electric motor, so we want to know the speed. I mean, is it 1000 RPM or 5000 or 5007 and so on. Or the position. If it is in that position, let's say 25 or 22 or 20 or and so on. So in mechatronics or the automated systems, if we use the signal elements, so we have to consider first of all what type of signals we need, what type of information we need about the actuators. And today we will discuss those type of signal elements which are providing signals. And so then, so one of them is the normal open switch and the operation. We'll discuss also about the operation. So one of them is it is operated by hand. So if you push this button here, so you see it's a normal open contact. That means the current we have here, let's take it out here. So we have here 24 volt. So 24 volt. We use 24 volt for the control system plus 24 volt direct current. It's connected here. And here we need, for example, the blue one here somewhere. This is the 0 line, ground. And here we can use the light like this. And if you connect that, first red one here has to connect it to the light, and then the blue one connected to the here. So if we push the button, here you see here they push the button. So let's say we have apply the force here. If we apply the force here, F, this contact gets closed, and since contact gets closed, then current is flowing, and then the light will turn on. So like this, so we have a light here, then it turn on. So okay, it's turned on like this, So, and you see here, it's a simple signal element actually, very simple. So if you push this button, you see here is 24 volt connected, and here goes through the circuit. So then if you push it, so we connect actually this 24 volt to this output, and this output connection terminal maybe go to the light. So like this, or go to the light. So, and like we have at home, turn on and turn off and so on. This is electromechanic switch. So we use that to operate the current to turn on and turn off. This is a normally open contact. So here we have a normally closed contact. That means normally it is closed. That means if we apply here 24 volt, let's say here we apply connected 24 volt here, 24 volt direct current, positive. So it goes through. Here, maybe from here, let's use the same color. So here, so in that direction, and could happen that we have a light here somewhere. So, and this light is connected to the earth here. So like this is here 0 volt. 0 volt, grounded, and we don't operate this push button. We don't operate this push button, but since it is a normally closed contact, current is flowing, and this light gets on. So light gets on. Like this. So if I push the button, if I push the button here, so what will happen if we apply the force? So then light gets out, turn off, because normally open contact gets, normally closed contact gets open, and then I interrupt the connections, the connection of the current, so the light gets on. So we learned that there are two types of contact: normally open contact and normally closed contact, used by signal elements. So the signal elements can have normally open contact or normally closed contact, or both of them. It's also possible. So normally open, normally contact, like this here. We say double contact. So this is like this, normally, normal, so it's not correct, so let's correct it. So use the, so normally closed and normally open, so this is normally closed. Let's say this is the 2 1. 1 2. Sorry. This is 1 2. This is 1 4. So this is 1 1. That means normally close contact 2 1, normal open contact 4 1. So both contact or double contact could be included in the sensor. Okay, so let's continue. Here we have as you see here we have here double contact. So normally. So I made a mistake. I have to correct it. Sorry for that. Okay. So like this here, we have 2 1. Normally closed, 4 1, normally open. So double contact. So changeover switch. Here you see once more, I'm in the normal open contact here, normal open contact. Here you see that, and normally close contact, and normally close and open together. And here we have different type of design. So this is momentary. That means if you push the button, you close the close the contact, and if you take away the force, I mean operation manual force F, so it gets open again. So, but here in this case, if you operate this so if you operate, then it gets closed. This is normally open, and you see here this is the important have a sign. So it gets closed. If you operate, it gets closed, and keep the position. So keep the position. Therefore, we say sustain switch. Keep the position. We have to operate once more to release it. So therefore, you see here the mechanic connections here. So there is a small ball here supported with spring. And you see there are two positions, this position 1 and position 2 here. Maybe I can show it with a pointer, the position 1, position. And if you operate this, so it takes this position or this position, depending on the position, it's normally open, gets open or closed. It is not normally open. If you operate it, gets closed. Okay, momentary, that means here, momentary, and this is sustained. And other type of switches like this here, so a different design. So different design, you see, but the same contact, I mean normally open, normally closed. And here we have also different type of normally open, normally closed switches. And here double contact, I'm here changeover switch, 1 to normally closed, 1 for normally open, and so on. You see there are different type of design comes from the companies. Each company tries develop their own design. Of course, there is a meaning behind that regarding the quality or safety and quality and so on. And again, normally open and normally close contact, normally close, normally open, and so on if you operate. And changeover contact, normally open, normally if you operate, normally the one connected to the 4. If we not operate, one connected to the 2, normally closed. And you see here normally open contact, normally closed contact, changeover contact, and mechanically linked contact. That means more than one contacts are mechanically linked. We can recognize from this dash line here, so that the contacts are mechanically connected to each other. If one gets closed, the other also gets closed. And here push button with normally open contact, manually operated by pressing. Here rotary switch, you see the check this is the sign. Rotary switch with normally open contact, manually operated by turning. And this is limit switch with normally open or normally closed contact, mechanically operated. Here you see this mechanical operated means that, so like this, it seems like this here, mechanically operated. Here we have such a sign. So mechanical operated. Okay, so you see here the mechanical operated double or changeover contact, and this is the design or the reset spring and housing and switching lever and guide pin and left spring and the contact spring and so on. So here we use a mechanical limit switch. This is an electric motor here. This is an electric motor connected with a screw spindle, and you see the electric motor is turning these spindle, screw spindle, and then this part is moving. I will show you now. This is moving part here. Huh? This is like nut connected to the screw spindle here, and since the electric motor is turning the spindle here, this screw spindle, and this is stationary. So this part, the yellow colored part, start to move. So, and we have here a sensor. Here the sensor, and sensor is checking the position. If say the moving part arrive this position, sensor will be operated like here is operated, and then if it is operated, so we'll give signals. Say the moving parts arrive this position, and so on. So that means, so we have here the electric motor, actually electromechanic driver or actuators, and then we use the sensor to check the position of this moving part. So is it there or is it not there, and so on. And relay, actually we discussed in this the electrical parts, and relay, you may remember, it is the relay, we need to operate several contacts like here. So those are the contacts here you see, and this is the coil of the relays, and if you operate the coil of the relay like this here, so then contact gets closed. If not, contacts are open. If you have changeover contacts, and normally closed, normally open. So by operating the coil of the by current, of course, by voltage, so operating the coil of the relays, we can change the contact, or relay change its contact. So relays, a relay has certain characteristic: low maintenance, able to switch a number of independent circuit paths, easily adaptable to various operating voltage, high operating speed. It means short switching times, so can be used as a logic or interlocking device. You see the relay contact configuration. So this is K1, means the coil, relay contact or relay 1. A1 has to be connected to the positive, and A2 has to be connected to the negative, that means the ground. So we have here 13. So this is once more here, maybe. So this is 1, means the number of the contact. Here you see number of the contact, 1, 2, and so on. And here also number of the contact. We have this is third contact, this is third contact. And the second number means the type of contact. This is, you see, 3, 4 normally open contact. Always 3, 4 normally open contact. And here 3, 4 normally open contact. If we see 3, 4, that means the normally open contact. If you don't see also the type of symbolic wise. So you see here the reed switch, we say reed switch, reed contact. We use to check the position of the cylinder, of the piston. This is the bar, this is the piston here, inside here. This is the piston, our piston. And this is the piston. This is the barrel of the cylinder here. Let's use this color here. This is the barrel here. This is the housing of the piston. And there is one thing more. So use maybe that. Now, this is the no, this is not seeable, but this is the magnet on that, the permanent magnet here. Huh? So it's black and not easy to color it. So magnet, and there's a reed contact here. You see, it consists of two metal parts here, and if the piston comes this position where we have the reed contact, so you see, because of the magnetic field, these two metal parts gets closed. So then the current can flow, and the LED, we can check via the LED gets on, and we can see that it is from outside. We can see from outside that piston arrived this position, and also using this cable we can get also the signals. We use these signals in our control system. And you may remember I talked before that. So one of them is the positive. This is the brown one. So brown colored, and the other one is the signals. So cable, I mean, this is black one, and the other one is the ground. This is the blue colored. So this is standard, huh? So, and those type of sensors. By the way, these type of sensor we say contactless sensor. So proximity switch. So it doesn't touch to the object we checked, we observed. But here in this case, we touched. I mean, you need the object touch and operate this this lever here, and then or here maybe we said we push here and touched, by touching we operate. But in this case here also touching, you see this mechanically operated. That means the moving parts touch this roller and operate the sensor or reed contact or the signals element. But here in this case not. You see here there is no direct touching. So therefore we say a proximity switch. And this proximity switch, the signal wise, symbol wise, we use this symbol here. So you see, and this symbol, that means here is the positive. That means you have to connect to the 24 volt, and here we have the blue. Here it is the blue. Has to be connected. This is the, say, the minus, and here we have the signal. This is the black one. Same. And there is another interesting sign here. You will see. So what is this one here? This is the magnet like this here. let's use the same color, black one. It indicates a magnet, U magnet, U type of magnet like this here. So, and that means this is a signals or the information about the type of sensors, and this is a magnetic sensors. This is magnetic sensors. So, and you can see also that this is also magnetic sensors, and this is also here same. You can also meet this type of sign. This is also magnetic sensors, and because of the magnet here, that means this sensor can check the magnetic field affected by the magnetic field, and therefore we get signals from this sensor. But those type of signals are, as you are seeing here, on-off type of signals, as you here indicated. So this is on-off type of signals. So, okay. So here, this sign means sensors. This means this is sign for sensor. Sensor, okay. Sensor, So, okay, and this here means normally open contact. This sensor has a normally open contact. This also has normally open contact. That means if sensor activated, then gives signals. If it is not activated, doesn't give signals. Like here, you see, is not activated because the piston doesn't arrive the position where we have the sensor. But here, the piston arrive this position where we have the sensors, and this is sensors active and the sensor giving the signals. So another pictures showing the same here. Again, we have 3 cables. This is the +1, and this is the -1, and this is the signals cable, so black. Okay, and we have here the magnet. You see here the magnet, and if the magnet arrive the position like this here, let's use that. Oh, no. So this is the that is the another color. Let's use this one here. So this is the magnet here, and it's also the magnet. And you see the magnet is here, and also the sensors affected, reed contact gets closed. So by the way, the reed contacts have in a tube, in a glass tube, 2 metal sheets. And these metal sheets are normally open. So if the magnets come near to these the metal sheets, they get close and they allow to flow the current. Okay, so pressure switch. So if we need a signal about the pressure, is there a pressure or not? Is pressure, let's say, the certain level or not? So we use pressure switch. So pressure switch are also very important in automation because we are interested to control this pressure. So therefore, we need signals about the pressure. So this is also a type of, let's say, the actuating. And if we check the actuator, that means the pneumatic pressure converted into the mechanical signals or into the electrical signals here, into the electrical signals. You see here the here mechanism. So if we have here no pressure, so no pressure, therefore this is not closed here. Let's use that and use this one here. It is not closed. You see here, this part and this part. But if I apply the pressure 14, you see this goes down like this here, goes down, and it touch this contact here and give signals from here. So, and by the way, this is the symbol of pressure switches. So we apply the pressure, pneumatic pressure or hydraulic pressure, depends. Then we get from the other side the electrical signals. And this arrow means here this pressure level can be adjusted. So that means if we can adjust this pressure level to the let's say this 6 bar or 4 bar or 3 bar, it is adjustable. Okay. So here we have inductive sensors. Inductive sensors. So what means inductive sensors? We will talk about. This is the pictures. So from the inductive sensor, and you see there is a thread on the sensors and nut. We can easily assemble that for a let's say for the sensor here, let's say like this one. It is so actually, so we cannot, but here, okay. And using this nut, it is not here, we can connect this to this mechanical part here. So, and it's like this, huh? And somewhere where we have to use, and and this is the surface we use to detect. This surface we use to detect here. And we will see how does it happen. So active surface, and here we have a LED. You see here is the LED here. So if it is active, we can check it by the LED. I mean here, if it is active, so we can see that. And this is the cable here. So on the cable consists of 3 parts, plus, minus, and the signals. So you see how does it work? So this is the schematic illustration. Here we have the sensor, and this is the object here, metallic object here. So if the metallic object comes down, let's say into the field of the sensors where the sensor can detect, so then sensor detect it and give signals. And the symbols of these signals and the inductive sensors is like this here, you see. And this is the symbol of the sensors, and something is missing. Actually, we don't know, is it here must be actually the more information, like is it a normal open contact or closed contact? We don't know, we cannot see from this picture, but we see this one is this is a coil like this, and that means this is an inductive sensor. The coil means inductive sensor. So where can we use the inductive sensor? To detect the metals, all the metal parts we use to detect the inductive sensors. For example, this is a linear actuator of or pneumatic linear actuator here, and this pneumatic actuator has a metal here somewhere, top of the piston rod, and if this metal come near to the sensing environment of these inductive sensors, the inductive sensors can detect and give signals. There's also such type of application in industry. We use the inductive sensors to check the position of the piston in that way. So another sensor is the capacitive sensor. You see here the capacitive sensor. What means capacitive sensor? You see here from this sign. This sign is also showing that this is a capacitive sensor. So capacitive sensor, and this is the sign of source. Also here we don't have any information about the normally open contact or normally closed contact. Actually, we need to the type of contact here somewhere here. Is it normally open contact or normally closed contact? You see the normally closed contact is like this, and this is the normally open contact. Okay, this is the object. If the object comes closer to the sensor, then sensor can detect it and give signals. So where we use the capacitive sensor, do you know that? What do you think? Nobody knows where we use the capacitive sensors. So capacitive sensors can detect anything without air. So it is the capacitive sensor is sensing everything actually without air. And this is okay. So then let's come to the actually, I had better slides. Now I have to check it. This is not I need more. So optical sensors. Let's use another one here. Okay, at the beginning we can say the sensors, this is more or less this summary. Sensors are classified as contact type, non-contact type, proximity sensors. Contact type sensors, proximity sensors, non-contact type sensors. So proximity sensors being the more commonly used sensors. So, and sensors are further categorized as either binary sensor or analog sensor. So binary or analog sensors. Binary sensors convert a physical quantity into a binary signals, which means it is two switching states, 1 or 0, and the most common being an electrical signals like on-off. And type of sensors, magnetic sensors, then inductive sensors like this, and here capacitive sensors, and this is continuing. And there is also magnetic analog sensors and magnetic binary sensors, and here with contacts and with contactless and pneumatic output and so on. And inductive sensor, we have analog and binary proximity sensors, and regarding the capacity, we have also analog and binary proximity sensors. And we continue, we have optical sensors, and now we will talk about the optical sensors. We finished the magnetic sensors and inductive sensors, but let's summarize it. And also the Optical position sensors we have as analog, as binary, but in opticals, in case of optical sensors, we have light barriers and diffuse sensors and so on. And for the light barrier, we have true beam sensors and the reflex with sensors, and the diffuse with fog and without fog and so on. And we have ultrasonic sensors used in the automation, mechatronics, and analog, also binary and proximity sensors. And also we have these binary sensors as ultrasonic binaries and ultrasonic sensors, barrier and ultrasonic sensors. So, and we have also pneumatic sensors. It's also interesting, in some applications, we need these pneumatic sensors. And these pneumatic sensors also is a pneumatic proximity sensors and back pressure sensors, reflex sensors, and air barrier sensors are 3 types of the pneumatic proximity sensors. So, and this we already learned, switch, limit switch. We already discussed that, the limit switch. You see here, how does it work? The reed contact. Now you will see the piston will move in that direction, and you will see. So what has happened? This is the reed contact, and the LED is not turned on, is not on, because the magnet is not near to the reed contact. But now you see here the piston is under the sensors. Without touching, I mean the proximity sensors, we said, therefore the contact gets close and then sensor deliver the signals. So you see here the brown 24 volt and blue is 0, and then black is the signals. And the reed switch we use on the piston linear actuator. Here the pneumatic linear actuator. You see here 2 sensors. On this here on the piston, 2 sensors. This is the LED. Here also to another position sensor checking this, the initial position. This is checking the advanced position of the sensors, and this is the cable connected to the sensors because of the electricity and the signals. So sensor switching distance is very important. In which this distance sensor switch. Let's say this is our sensor here, and this is the LED on the sensor, and this is the object, and see what's happened. So, and this is the SN, the switching distance, normal switching distance. The distance is not, I mean, sensor is not active, and the distance between the object and sensors, and SN is switching distance. So then let's have this H here. H is the hysteresis. So that means the sensor detect in this distance here, in this distance sensor detect if sensor gets closer to the object here in this distance. Sensor detect, that means the LED gets on, but if the object moves in that direction, the LED gets off after this distance SN plus H. So, and this is H is the hysteresis we call. So that means the sensing distance and the touching distance and getting if sensor let's say the move away from the if object move away from the sensors, and the switching point is this SN plus H. If object near to the sensor, switching point is SN, in the distance of SN. So this H is the hysteresis. So we have to consider that we don't lose the signals in this distance if object moves back its initial position. So, inductive sensor, we already discussed. Inductive sensors are for the metals, and you see here how does it work. So this is the object here, comes near to the inductive sensors, and the inductive sensors gets detected, and you see the LED gets on. So here, in that case, so there is no, the LED is not active, but you see here the oscillation. There's a current, oscillating current with a certain amplitude inside in the electronic eye, and it goes. If they detect it is getting zero, it starts with a certain amplitude, and if the object gets closer to the sensor, it gets zero, and since it gets zero, then the sensor recognizes and say there's something I checked, so I detect, and you see the signal gets on here. Huh? So the sensor output signals gets on and deliver the signals. On inductive proximal sensor, the bigger the coil, the greater the active switching gap. So inductive sensors can only detect metals and different switching distance for different metals. And you see the inductive proximal sensor, I mean the circuit diagram here. How does it work? And you see the parts here. And power on inductance created, distributed when conductive, metals, materials present, analog, and so on. Huh? So I will not mention it one by one. Those are the parts here explained. So here you see the inductive proximity sensors. We said the metal parts can be detected by inductive proximity sensors, and depends on the type of metals. We have different reduction factors for the signals. So milled steel is one, that means the maximum, and the chrome nickels in 70%, 90%. Regarding to 100%. So brass is 0.3550 and aluminum 0.3550, and then the copper is 0.25 till 40. That means the sensing power is getting lower in that direction. So because in that direction, sensing power or capacity getting lower. Here we have 100%, let's say we take it 100% here, and here we have, let's say 25, we have here, okay, 25 or 40%. Okay. So depending on the type of metal. Okay, here, so the inductive proximity sensors, sensors detect metals and operate quickly, reliably, and tireless. They are used to count, identify, detect, switch, control, check, distinguish, sort, position. So for those type of let's say for those type of targets, we can use inductive sensors. And there are some examples here, inductive proximity sensor where we can use. You see, sensing a CAM controller. So there are here the CAM. You see CAM here. This is here first one, and this is another CAM here. You see in different angle, based on this axis here, different. So you see here, I can indicate it. So use another color better here. This is this angle here, and this is this angle here, you see, and this is this angle here. So, and this is the rotation, as rotation here. Let's say it is rotating like this here. Rotating like this. So, and you see here we have also the sensors. Here we have the, where is it? No. Okay. Formula, another color, use another color. Here we have the sensor here. Those are our sensors here. And here we have another sensor. And here we have another sensor. So, and depending on the angle. So here let's say this sensor gives, let's say this is the one, and this is the one, and this is 2, and this is 2 here, and this is 3, and this is 3 here. If sensor 1 gives the signals, that means the rotary, the shaft is in this position 1. If sensor 2 gives the signals, that means the shaft is in the position 2. And if sensor 3 gives signals, that means the shaft is in position 3. So it is very interesting. They use frequently in the industry to check the position of a rotating part, mainly the shaft. And we also decide and apply certain command based on the position of the shaft. Okay, and another application for the inductive sensors we have here, you see, this is our sensor here, and we have here the gear system, and this gear system have gap and gear, so measurement of speed and direction of the rotation. So we have another sensor here. So, and using these two sensors here, let's say this is the sensor 1, and this is sensor 2, and using these two sensors, we can calculate the rotation and the direction of the rotation. Rotation, that means the speed of the rotation, RPM, and the direction. Is it turning in that direction or is it turning in that direction? And the RPM. So here in this application, we see if we are checking the end position of a semi-rotary actuator. This is a semi-rotary actuator. That means it is moving, let's say, in that direction or in that direction, semi-rotary, and it is restricted. Here there are some cams and connected, or some cams and also sensors here we used to detect the position. You see the cam here. This is the cam. I will indicate with different color like this here. This is the cam here. So, and now the sensor 1 is giving the signals. The sensor 1 is giving signals, and the control system know that the actuator, semi-rotary actuator, is in that position, and if turns in that direction and arrive these sensors, sensor 2 then sensor 2 will be active, and then the controller gets information that the semi-rotary actuator arrived its position 2. So you see, we need the sensors to observe and to get information about the motion of the actuators. So this information is very important for the control units, because if we don't know anything about regarding the motion of the actuators, could be position, speed, and torque, and force, and many things. So the control system cannot decide what to do. So we need information. So like we human, we have ear and eyes, and we can touch and get certain information, and this information flows via our nerve system into the brain, and brain can decide so what to do. Is it hard, or is it cool, or is it, I don't know, far, or is it near, and so on. So, and decide, and according to decision, we do something, and this is the relation between actuator, sensors, network, hardware, and software. Okay, so inductive proximity sensors we use also detecting and position of a press. Let's say we have a press here, pneumatic press or hydraulic press, and it moves up and down like this here, up and down, and so on. And we checked here using a sensor, is it down or is it up, and so on. Or inductive sensor, we use here the, say, the metal part and the top of the piston rod, and we already discussed it, you know. And this is another sensor, the capacitive sensor, already we discussed. You see here the parts of the capacitive sensor. And so the front part of the capacitive sensor, that means the touching part, surface, sensor is looking for a change in capacitance in the active field. So this is the active field. So capacitive proximity sensors, where we can use that, the application of is that the almost similar to the inductive sensors, able to detect most materials, so switching distance adjustable, able to detect fluid level through the valve of a bottle. We will have an example and we'll see that. So okay, let's make a break, huh? This is 15:25. So let's make 15 minutes break, 15:25. So on 10 to 4, we will start again. 10 to 4. Okay, let's continue. So, can you hear me? Okay, now, so the capacitive sensors, we said, so where we use the capacitive sensors, we learned already inductive sensors. Now let's continue with the capacitive sensors. So capacitive sensors. Almost similar to the inductive sensors. Okay, we already talked that. No. Choose the okay, capacitive, we talked this part. Almost similar to the inductive sensors, able to detect the most material, switching distance, adjustable, and able to detect fluidic level through the wall of a bottle. So here you see the inductive sensors, and you see also the cables connecting, the plus, minus, and then signals part, brown, blue, and black, and so on. And here you see the LED, for the sensors, if it gets active and the LED turn on. And if the targeted object, the objects gets closer to the sensors, here the front part of the sensor, and you see then the LED gets active here. That means turn on. We have the light. Okay, and here we have an application. You see the capacitive sensor are used to detect the level of the fluidic here. There's a fluidic coming, let's say, from this pipe here. And let's have that. Okay, coming from this pipe here. So in that directions, okay. And into the reservoir here. And if it is arrived, if the fluidic or water, let's say the fluidic arrive this level, then sensor gives signals. And sensor is adjusted to so that it does not see the wall of the vessel. So there's a wall here of the vessel. You see, this is the. Let's use another color here. This is the wall of the vessel here, but sensor doesn't see the wall. Sensor is adjusted to check the level of the water inside of the wall here. So, and like this here. Okay. Oh. And here you see if the fluid arrive the let's say the sensing point of the sensors, so sensor deliver the signals, and the controller understand that the water arrive its limit position and final position, final level, let's say, and I have to stop to deliver water anymore. So the capacitive sensor detection of matte and black objects, both of them. Matte and black objects can be detected. or detect fluid level, wall thickness must be limited if we use for such applications. So monitoring the winding of electrical wires and the cables. So you see here the circuit of the capacitive proximity sensors, and the parts are here indicated. Let's say the one is the power on, and nothing happens, capacitance created when material presents, and 2 is here. So the 2 is the analog to binary signals converter, and so on. So where we can apply the capacitive sensor, capacitive proximity sensor, you see there's shoes on the band moving, let's say in that direction here, so in that direction, and you see there's a sensor here, we can check by the sensor. So we learned magnetic sensor was, let's say, sensible about the magnetic field, and inductive sensor was sensitive about the metals, but is a shoe, and so we want to check the shoe, and therefore we use the capacitive sensor here. So another application here we can use to check the fluidic in the minimum level and the maximum level, and so on, in a cup. Or we check the bottle in a carton here, packing 4 pieces in a carton, and we have checked. We use the force sensor. This is existing, and this is existing, and so on, and the fourth one. So therefore we use force sensor. Let's say 1, 2, 3, 4. If all of them are active, so that means they all 4 bottles are in the box. Another application, we use the these capacitive sensors here. This say let's say the metal sheet or flowing any paper or anything. So, and it is moving, let's say between these two position, normally must be in the middle. So then we checked using the capacitive sensor, the position, this is fluctuating. We can get any information about any fluctuation, and therefore we can increase or decrease this force here. This is the force here. You see it has a certain force applied. To keep this the flowing material in the middle position, like you see here, the black one. So this is the normal position. So in that position, but it is fluctuating between these 2 limit position, the position 1, I say the position 1 and position 2. And getting this information, we can change the force here applying, and we can avoid the fluctuation. Okay, now the next one is the optical sensors. We learned magnetic sensors, inductive sensors, capacitive sensors, and now we will discuss the optical sensors. So the optical sensors, there are 3 different types. There are 3 different types of optical proximity sensors. So one of them is the true beam optical sensors, and the second one, retroreflective optical sensors, and third one, diffuse optical sensors. The optical sensors use the light, detecting by the light. And the optical proximity sensors, we said the optical proximity sensor can be divided, true beam sensors and the diffuse sensors. And the true beam sensors designed with the fiber optic cables, and diffuse sensor also designed with fiber optic cable, and the optical proximity sensors retroreflective doesn't have. So we will discuss all of them. So mainly the optical sensor consists of two parts. So true beam sensors consist two parts. That means the transmitter and receiver. So this part transmit the light, and this part receive the light. So this transmit and this receive it. And then by receiving, they communicate and they say, okay, I'm receiving the light. That means there is nothing in between. So there is nothing in between here. Huh? There is nothing in between. So if there is something in between like this, that means the beam is interrupted. So the receiver cannot get the light, and then the contact is broken. So the sensor gives signals, gives signals and deliver the information that there is something in between. This is the working principle of true beam sensors. And you see here, this is the transmitter and this is receiver. This is here transmitter and this is receiver here. So, and this is the object in between, object. So if object goes through and interrupt the transmitted light to the receiver, so then the signals give, sensors gives the signals. So like this here, huh? We can easily see here, there is the transmitter is transmitting the light so to the receiver, and receiver gets the light. Of course, this is a beam like this here. Huh? So there's a beam. So, and if any object gets closer to interrupt the beam in between, so you see, so the LED gets on here. There's a LED here, you see. Here there's a LED. So LED is not on. So LED is on. Sorry, and here is also the LED. These two LED means it works. I mean, it works. And there is nothing in between. But if we get this LED, the open here, this means it is active now. So you see, there is no, this LED is not active, but this two is active, this one and this one. That means it works. So the transmitter sent the light and receiver is getting the light. That means it is okay, it is working, but there is no object in between. If there's an object here, then you see this yellow one gets also active, and then we say, or the signals, the sensor delivers signals for the detection. And this is the circuits here regarding the emitters, the true beam sensors, and this is the receiver emitter, that's mean transmitter, and this is the receiver circuit, and you see the parts here explained. And these true beam sensors, we use advantages of true beam sensors. So what are the advantages where we use mainly? So let's say enhanced reliability because of the permanent light during operations. That means we have a permanent light, and if something goes in between, that means interrupt the permanent light, so the sensor gives signals and say there is something in between. That means sensors deliver also signals in case it works. So, and therefore, this is reliability is, much more important here. So wide range we can use for the wide range because we have here the transmitter and here we have the receiver. So receiver and transmitter, and there's an important distance. Important distance in between, and this distance we cannot realize with inductive sensor or magnetic sensor or capacitive sensors. This is an important advantages for true beam sensors. And the small objects can be detected even at large distance because of these reasons. So suitable for aggressive environment. So if you are in an aggressive environment, it doesn't matter. So there's a true beam, and if true beam is interrupted, so the sensor delivers the signals. So good positional accuracy. So we use it as also as analog sensor, and then we can get information about the position. The distance. So therefore, good positional accuracy. So what is the disadvantages of beam sensors? So disadvantages of beam sensors is to separate proximity sensor modules and separate electrical connections are required. So because here we have transmitter and here we have receiver. So receiver, to separate body or to separate sensors, and each of them must be supplied by the by the electricity. So cannot be used for a completely transparent object. So if you have a transparent object, let's say the glass in between, glass we cannot use it because for completely transparent object. So that means we cannot detect the transparent object because the light can go through transparent object and we cannot recognize it. So true beam sensors, applications of true beam sensors used as safety devices. Safety devices like today's in the companies where we have safety problem, like if we operate the press, and press must be operated by two hands, where they are two-hand operation. But even if we have two-hand operations, so we use the true beam sensors that the operator to control the operator, because the operator sometimes by forgetting can put his or her hand into the direction of the press where it is working and can damage hands and so on. But if you have a true beam sensors detecting the front part of the press, so then it is not possible, because that means if sensors give signals that the light is interrupted, so then the press can immediately stop the motion, so they avoid any danger. So fast continuing applications, fast counting applications. So the counting is interesting phenomena. The counting we use in automation or the mechatronic to count, the quantity and the amount. So, but The sensors, we can use also different sensors, like we explained for the sensors or inductive sensors, but the frequency, I mean the speed, is also important for the counting, and the light is much more, higher. It's offer much more higher counting, fast counting. Therefore, here is indicated as a application. So monitoring for broken parts. If a part is broken, so we can easily detect by using the TrueBeam sensors. Like, let's say we have a drilling tools here somewhere. Drilling tools. So, and here we have a sensor, transmitter, and receiver, like this. And we have here TrueBeam. So TrueBeam is interrupted. So because of the drilling tools. So, but if it is broken, the interruption stops, and then sensors give signals. So by this the working principle, so we can easily understand that something is wrong. That means the tool is broken. So since tool is broken, so then we have to change it. We have to go there and change it. We can get the signals. Okay, here there's an example. You see, TrueBeam sensors. This is the transmitter part. This is the receiver part, and here we have the drilling tools, and so it interrupts the light. You see here the light is interrupted, but we can use the sensor in that way. If sensor doesn't give any signals, that means that everything is okay. So if sensor gives signals in this case, in this application, so that means it is broken here in between. If it is broken somewhere here, so then that means so these signals go through, and then we can understand that the tool is broken. Or we can use here in press applications, I guess the hydraulic press, and we can use here the sensors and say TrueBeams like here. If I mention it, so TrueBeams. So in between there is we can use a light here in between, and if operator is a light beam here in between, so if operator, let's say they try to put its hand so in that direction and interrupt the light, so press stop immediately and avoid any danger. So another type of optical sensors is the retroreflective sensors. Retroreflective sensors has also its, let's say, the own application, and the important part is the retroreflective sensors has the two parts on the same body. That means here the transmitter, you see here the transmitter and the receiver on the same body. So that means the transmitter transmit the light, and there is a reflector somewhere, and it reflects the light, and the receiver gets it. So we need a reflector like this here. So this is the reflector here. And the benefit of these let's say the type optical sensors, we have transmitter and receiver in the same body housing, and but we need a reflector, the prismatic reflector, to reflect the light and send to the receiver. So the way of function or the is like this. We have here you see the transmitter like this, and you have here the receiver on the same housing like this. So, and if object goes through and interrupted like this, so if object goes and interrupt the light in between, so then you see this yellow LED gets active. This part gets active. This is already active because the green one means that sensor is okay, it is working. So, and the yellow one means if yellow is active, that means sensor detect an object in between reflector and the sensor. And here you see the circuit of the retroreflective sensors consists of the 12 parts, and all the parts are here indicated. And the retroreflective sensor, the advantage of the retroreflective sensor, what are the advantages? Maybe let's talk about what is the advantage of retroreflective sensors. The enhanced reliability because of permanent light during operations like true beam sensors, and simple installation and adjustment. The installation is simple and adjustment also simple. Objects can be diffuse, reflecting, mirroring, or transparent as long as enough light is absorbed. And a greater range as compared to diffuse sensors. There's diffuse sensors, they have a greater range here. Disadvantage of retroreflective sensors is transparent. It's transparent, very bright or shiny objects may remain undetected, like we talked in the true beam sensor. So shiny objects which cannot, or transparent, highly transparent sensors, object can let the light through, and we cannot detect it by these sensors. So the applications where we can apply, so you see here there is a retroreflective sensors used here, we use here. This is the body of retroreflective sensors here. And this is the reflector on the other side. This is another color. This is the reflector here. So, and the objects are moving on this band here, on this band, moving in that direction. So, and each box on this band interrupt the beam and light beam in between, and then the sensors detect and deliver the signals. So we can check how many parts are passing over this band, over this transfer band, and we can count it, or we can say there is no bugs coming, going, and so on. Mainly, we use it counting of objects. Another application for retroreflective sensor is, so another application could be, So we have a paper like this. Here paper is, let's say, flowing from one position, from this position into the two. And of course, to avoid the stress in between, so we have a certain how to say, deflection. So, and to check it, we use three retroreflective sensors. We have here the sensors 1 and sensors 2 and sensor 3, and we have here the reflector. And if sensor 3 is active, that means it is too much. If sensor 1 is active, it is too less. So if we get the signals only from the sensors 2, that means it is okay. That means it is in between 1 and 3, so it is acceptable. So slack control. Okay, the diffuse sensors, okay, we already discussed it. So another sensor is the diffuse sensor. So this diffuse is reflected by the object. Light reflected by the object here, you see. So the object is not there, and the same transmitter and receiver in the same body, and its transmitter already gives the light into the environment, and if the light is not reflected from or by any object, that means there is no object in detection. But if the object is, let's say, the interrupt the light somewhere, and let's say the light is reflecting by this object and into direction to the receiver, and receiver gets light from the object, so then we can say also there's an object in between. So interrupting the light or sending the light back to the receiver. This is the last one of the optical sensors, and it has also certain advantages and disadvantages. Let's talk about the advantages of these diffuse sensors. Because of the reflection of the object activates the receiver, and the additional receiver is not required. So this is an advantage. So diffuse sensors allows frontal detections. Objects can be detected selectively in front of a background. So disadvantage, what could be disadvantage? So they are not as suitable as true beam sensors if accurate lateral response is crucial. Or they do not react to objects with reduced reflection. That means black object. If there's a black object, I mean here, you can imagine if you have a black object, so unfortunately, there's a black object now in the picture, but black object, you know, it gets the light and doesn't reflect the light. So the object must reflect the light. If the object cannot reflect the light, so we cannot detect it using by these diffuse sensors. Okay, the application of diffuse sensors we can use, as you see here, there are some sensors. This first one and the second one here, and they are using the position of these parts. Is it here so top, or here is the down? You see, this is the down here, top and down. So we can get the information about the position of these work pieces moving on a band. Is it in that position or is it in that position? And I would like to repeat it. The important is that the object has to reflect the light coming from the transmitter, reflect to the receiver. So the diffuse sensor we use to also check the geometry of an object, like here we can check this corner here, and we can check this corner here, or this corner using the sensor, and this corner. And by the way, we can check the shape if it is enough for us. 1, 2, 3, 4, 5, and we have another here behind this one. So using these 5 sensors, 6 sensors, we can control 2, 4, and 6 corners of this object, and we can give information about the geometry. Let's say if all of them are inactive, that means doesn't see the corner, or or see the corner. So that means we have the information about the shape of the materials. So it depends how we organize the sensor and how many we use a sensor to get information about the shape of the object. So fiber optic cables. What means fiber optic cables? The fiber optic cables we use, in optical sensors. Why fiber optic sensors? What is the advantages of using fiber optic sensors is following. So I'm sure you know what is fiber optic cable. So detection of objects in areas of restricted across a very small area, let's say space-wise, very small, and you can use the fiber optic cable. I will show the example, and you will understand much more better. So detection of an object in areas of restricted access. So this is the explanation for that, or possibility of remote installation or accurate detection of small objects, or sensing elements can be moved. So you see, this is the sensor, our optical sensor, and there's a true beam sensors, and we can use the fiber optical cable here, and we can bring this object, the emitter, transmitter, and receiver, like transmitter here and receiver here, connected to the fiber optic cable, and we can transmit the signals via the fiber optic cable into the main body of the main sensor. We can use in that way that they are separated, and we check the object whether it is in between or not, or we can use it in the same let's say the same body, and we use the possibility reflecting by the object. That means the transmitter and receiver are on the same object here, and the light must be reflected by the object, so that the receiver gets signals and gets the light and deliver the signals for the detection. like this here, for example. This is fiber optic cable. So this is the object, and this is the emitter fiber optic cable, and this is the receiver fiber optic cable on the same object here. So then we can check detect the object if we need. And you can use it in a very small area, restricted area. And this is the important advantage. Like here, you are checking, let's say, this part here. So using this fiber optic facilities, the sensor is somewhere under the system, and here taking by the fiber optic cable the sensor here, and you can check it. Or in SAW machine, you can share it. So you can check the so I forget the name of this machine, fiber optic, but you know that we use it at home. And you see this one part is here down and the other part is up here. So in between the stuff and the material, and you can check is existing or not existing. And here you can check the parts, screw cut or not. Screw cut it or not. It is also possible to check using these sensors. And here we use to check the workpiece here again in a small and restricted area. Okay, now we came to the ultrasonic sensors. The ultrasonic sensors. So we finished the optical part, optical sensors. What we learned: magnetic sensors, inductive sensor, capacitive sensors, and the optical sensors. Now we came to the ultrasonic sensors. You know, the ultrasonic sensors is sending voice and in a certain frequency and for certain power, and checking feedback and giving signals accordingly. So this is the ultrasonic sensor. We can use the ultrasonic sensor as an analog sensor. So that means we can measure the distance, not only the existing or not existing. And this is the object here. And you see, this is the object we have here. So, and this is the noise or the voice is created by the ultrasonic sensors to the environment, and sound. The sound is created by the sensors, and this is the accepted angle of sound. It is like here you see the accepted angle. Okay, to detect the object. So what is the advantages and disadvantages of the ultrasonic sensor? First, the advantages of the ultrasonic sensors is the relatively large range regarding the measurement or the getting signals. Object detection irrespective of color and material. So the color and material doesn't mean anything regarding the sensing, because the sound used here to detect the materials. So sound is not, let's say, sensitive about the color and the material, type of material. Safe detection of transparent objects, but transparent object has to reflect the sound, of course. So relatively dust and dirt insensitive. So not sensitive about relatively not sensitive about dust and dirt. So dust and dirt is also important in certain environments. We need those type of sensors, and the certain environments are affected by dust and dirt. Fading out of background possible. The fading out of the background is also possible. Outdoor applications possible. Okay, what is disadvantages? Let's come to the disadvantage of ultrasonic sensors. Object surface should be at right angles. At right angles because the light, the sound must be reflected. I mean, right angle means if we have our sensors here somewhere and sensors is distributing the sound, so this must be right angle, like this. They reach slowly. Okay, the sound is not as fast as the light if you compare to the optical sensors. They reach, they react slowly. They react slowly. Light is much more fast. Generally, more expensive than optical sensors, and then not detect sound absorbing materials. So there are some materials absorbing the sound. On those type of materials cannot be detected by the ultrasonic sensors. So you see we have some example here regarding the applications. We have paper. You see paper or sheet metal could be flowing, let's say, from the station 1 into the station 2. So it is flowing like this. Okay. And we are checking the slack here. So we are controlling the slack. So you see here we use, where is it? Where was that? Somewhere here. Here. So slack, we control the slack using 3 sensors because those are the on-off sensors, existing or not existing, on or off. And we use 3 because the first one must be always active, third one mustn't be active, and 2 must be active. So then in between, so we are checking that is in between, and therefore we decide, okay, this is okay. But here you see we use only one. Here we use only one because it is analog sensor. We can measure the distance. We can measure the distance. We can say in this distance, so this distance is acceptable. Let's use the column up. Okay, this is the distance here in between. Say a reference value. So here, say the H in this distance is okay. Not less or not more, in a certain tolerance, of course. Okay, so we can also use to sort. So to sort, let's use another color. So to sort, I mean this part. You see, these parts have different dimension regarding the height. Here in this example, we have 2 different dimensions, or 2 or 3, I don't know, maybe 3. It seems 3, so on using these sensors, we can detect all these surfaces, and also since this is a reference, this is the reference surface. Let's use another color. Here the reference surface is this. This is the reference surface. So we can get information about the thickness of the material flowing. So on this band, let's say in that direction. Because it's the analog sensors, we get the information about the distance. So not only existing or not existing, how much, how many, huh? Okay, and monitoring of the batch thickness also we can use for the thickness here to measure the thickness, like we explained in previous example. And we came to the pneumatic sensors. So I would like to stop here because next week we will maybe one lesson, or let's say the half of the lesson we will spend for the pneumatic sensors, and we will finish the sensors, then we will continue with the network. So I think this is enough for today, and I would like to remind you for the homework, please, maybe so let's wait for so the pneumatic sensor. Okay, we had here somewhere our homework, huh? Actuators, okay. Where is it? Homework, okay, here. So I would like to remind you that our homework here, we shaped already the groups. The group A, Group B, Group C, Group D, E, F, G, and so on. And all of them know actually its homework is already defined here. Where is it? So here the group A, pneumatic actuators, B, hydraulic actuators, C, electromechanical actuators, D, sensors, E, network, F, hardware, and G, software. So, and also what is the expectations. So each group has to prepare a presentation about design of the topics to include it, product, functions, how does it work, applications, typical applications, advantages for what type of application is used, or disadvantage for what type of applications we don't prefer to use, and so on. So do you have any question? And date is also mentioned somewhere, huh? Our deadline, where is it? Here. Deadline is 24th of April 2023. PPT documents, presentation, question, following presentation. This is the evaluation. So we will evaluate in 3 points: PPT documents, presentation, and question after the presentation. Question means I will check whether it is copied or it is understood. Okay. So, mid-exam will be online or face-to-face. So, according to my information, face-to-face, not online. Okay, I will share you the presentation slides for the electromechanic and sensors. So then next week, I guess we will finish also the network part, and I will deliver also the network slides on the Orlean platform. Any question? member of homework, and I already explained it here. This is the group A here, and this is the group B, and group C, and group D, and group E, and group F, and the group G. Okay. So, have a nice week and bye bye.
Hocam,
Efendim?
sorabilir miyim? Ben makine teorileri dersini de sizden alıyorum da oraya içerikleri yüklemişsiniz ama açılmıyor. Sadece gözüküyor.
Makine teorisinde içerik yok.
Ha, evet,
Orada
yani ben
bunları koymuşuz. Onunla ilgili kitap tavsiye ettim. O kitabı okuyacaksınız. Kitabı alacaksınız.
kitabın ismi neydi acaba?
Onu yayınladım ben arkadaşlarla. Anlattık bak. Bir dakika. İnternetten indirebilirsiniz onu. Bir dakika. So, this is the mechanics and machines. Applied kinematic analysis. 4th edition. David H. Maiska.
Tamam hocam,
Okay.
teşekkür ederim. Teşekkürler, iyi
Rica
günler.
ederim. İyi günler.